The silent chemistry that keeps your phone alive. Every swipe, every tap, every glowing screen depends on reactions you never see. Your phone survives each day because chemistry quietly holds itself together. And when that chemistry slips, everything shuts down. To understand why your phone works at all, we need to look inside it, not at screens or circuits, but at energy trapped in motion. Modern life runs on portable power, and portable power is a chemical illusion of control. Lithium-ion batteries do not store electricity. They store potential, waiting to be released. The distinction matters more than it might seem. Electrical charge stored as a static field behaves differently from chemical potential stored in the arrangement of atoms. This matters now more than ever. Phones are thinner, faster, and always connected. They charge quicker and drain harder. Each demand pushes battery chemistry closer to its limits. What feels like convenience is actually a delicate balance, one managed reaction away from failure. At first, the process seems simple. Plug in the charger. Energy flows. But inside the battery, something more precise happens. Lithium ions begin to move. They migrate between layers, guided by electric fields. This movement stores energy chemically, not electrically. Nothing burns. Nothing sparks. The reaction remains controlled. That is the first beat, a reversible reaction designed to repeat thousands of times. The second beat follows quickly. Electrolytes stabilize ion movement. Separators prevent short circuits. Every component exists to keep chemistry predictable. When balance holds, the phone lives. The electrolyte, typically a lithium salt dissolved in an organic solvent, is a medium through which ions travel between the two electrodes. Then comes a third beat: heat, usage, time. Each cycle slightly alters a reaction. Ions lose efficiency. Structures degrade microscopically. The system still works, but it is changing. The changes are invisible to any external inspection of the phone. The battery still charges. The screen still turns on. You experience none of this directly. The phone still turns on. The screen still responds. But beneath the glass, chemistry is quietly counting cycles. And that is where the story begins to shift. Each charge and discharge leaves a trace. Not visible, not immediate. Lithium ions do not travel alone. They drag solvent molecules. They interact with electrode surfaces. Over time, these interactions reshape internal structure. Layers thicken. Pathways narrow. Resistance grows. The solid electrolyte interface, a film that forms on the anode surface during the first charge cycles, is initially protective. It stabilizes the interface between the electrode and the electrolyte. At first, the battery compensates. Voltage remains stable. Performance feels unchanged. The chemistry adapts by working harder. This hides degradation from the user, but adaptation consumes margin. The reaction becomes less forgiving. The system is now operating closer to its limits without the user being aware of it. Heat accelerates everything. Fast charging increases ion speed. High temperatures amplify side reactions. Electrolytes slowly decompose. Protective layers form, then crack. Each crack exposes fresh surface. More reactions follow. The relationship between temperature and degradation rate is not linear. Elevated temperatures can double or triple the rate at which side reactions occur, compressing months of normal aging into weeks of high-temperature use. Here is the early conflict. The same chemistry that makes phones portable also makes them fragile. Lithium is small, fast, and reactive. It delivers energy efficiently. But efficiency trades stability. Every shortcut tightens tolerances. The design choices that allow a battery to deliver high power in a thin, lightweight package are the same choices that leave it less resilient to the conditions of actual use. Modern phones demand more cycles in less time. Streaming, gaming, constant background processing. The battery never truly rests. The reaction stays active. Even idle states require chemical work. There is no full pause. Background processes, location services, push notifications, network monitoring, sensor polling ensure that the battery is continuously supplying small amount of current even when the screen is dark and the phone appears to be at rest. Manufacturers fight this with control systems. Software limits charging speed. Thermal management disperses heat. Battery management predicts failure before collapse. These systems stretch chemistry as far as possible, but they cannot rewrite physics. They can optimize the conditions under which the chemistry operates. They cannot change what the chemistry fundamentally does. What nobody expects is how suddenly limits appear. One day, the phone lasts all day. The next, it struggles. The chemistry did not change overnight. It crossed a threshold. The threshold is real. There's a point in the degradation curve where the accumulated loss of accessible lithium and the increased internal resistance combine to produce a step change in observable performance. Below the threshold, the battery copes. Above it, the coping mechanisms are exhausted. That threshold forms silently, layer by layer, cycle by cycle, until balance tips. And from that moment, decline becomes visible. This is where the hidden conflict sharpens. Because battery failure is not a single event. It is the accumulation of microscopic decisions. Each charge cycle leaves fewer paths open. Each discharge pulls harder on weakened structure. Inside the battery, lithium begins to misbehave. Ions no longer move cleanly between layers. Some become trapped. Others played onto surfaces as metallic deposits. These deposits reduce capacity. They also increase risk. The reaction grows less predictable. Lithium plating. The formation of metallic lithium on the anode surface rather than its proper intercalation into the electrode material is particularly concerning because metallic lithium can form needle-like structures called dendrites that can penetrate the separator and cause a short circuit. Energy chemistry now faces a paradox. The harder the phone works, the faster chemistry degrades. High performance demands high current. High current amplifies heat. Heat accelerates side reactions. Side reactions steal usable energy. The loop feeds itself. The feedback between performance demand and degradation rate means that the phones most heavily used are also the phones whose batteries age fastest. The users who need the most performance get the shortest battery lifespan. As degradation continues, internal resistance rises. More energy is lost as heat instead of power. The phone compensates by drawing more current. This worsens stress. Battery management systems intervene aggressively. Performance throttles. Charging slows. The user feels inconvenience, not chemistry. The throttling is a genuine attempt to protect the battery from conditions that would accelerate its decline, but it creates a user experience that feels arbitrary without understanding the chemistry driving it. Yet, the chemistry feels everything. Electrolytes thin. Electrode surfaces roughen. Mechanical stress fractures layers. The battery is no longer a smooth reaction chamber. It becomes uneven terrain. The uniformity that allowed ions to move efficiently through the battery in its early life is gone. Current now flows through whatever pathways remain, concentrating stress in the areas that are still intact and accelerating their degradation. Here is the emotional peak building, because this process is unavoidable. Even perfect care only delays it. Lithium-ion chemistry trades longevity for density. We chose convenience over permanence, and the battery obeys that choice faithfully. The trade-off was made at the design stage by engineers optimizing for the metrics that matter most to the market: energy density, weight, charging speed, with longevity as a secondary concern. Nothing dramatic happens inside the phone. No explosion, no warning, just declining output, shorter days, longer charging times, sudden shutdowns under load. This is chemistry honoring its contract. Energy was borrowed. Now it is being repaid with interest, and that realization leads directly to the final moment. The climax is not failure. It is inevitability. The silent truth is that your phone is alive on borrowed chemistry. Every charge trades a fraction of tomorrow for today. Every fast refill accelerates reactions meant to move slowly. The battery does exactly what it was designed to do: deliver energy efficiently, then fade. This reframes how we see technology. Battery decline is not poor engineering. It is chemical reality. Lithium-ion systems balance power, weight, and speed. Longevity was never the priority. Portability was. And chemistry enforces that decision without compromise. The resolution is awareness. When you understand the reactions, behavior changes. Heat matters. Charging habits matter. Rest matters. Not because they stop degradation, because they slow it. They give chemistry time to recover between cycles. This insight extends beyond phones. Every modern device relies on controlled chemical debt. Laptops, cars, grids. We live inside systems that spend future stability for present performance. Batteries make that trade visible. Once you see it, the phone feels different. Not fragile, but temporary by design. A precise balance of reactions holding together just long enough to matter, long enough to serve, then gracefully decline. The silent chemistry keeping your phone alive is not failing you. It is completing its promise, exactly as physics intended. So what do you think? Are we repeating the same mistake again? The